Okay, but stop what you're doing just for a quick second. I want to go through just a couple quick examples of the new problems, the setup problems. These are meant to be easy. So pop those closed. Let's just take a second and let's get back to work. So what about something like this, where here's the situation. A helicopter decreases speed while moving straight upward. The air exerts a lift force L on the propellers. Ignore air resistance. Okay, so we're supposed to use these conventions, right, and come up with the equations of motion. So we want to know what's the x component of the net force and the y component of the net force. Right? So what is this? This is just a free body diagram problem, isn't it, really? This is a one-dimensional problem. There's not much going on. What are the forces acting? Gravity. Okay, so we've got mg pointing down and lift force, right, which we call L, pointing up. And it just looks something like that, wouldn't it? Okay, does the fact that it's decreasing speed really have any impact on this? No, not really, right? I mean,
Wouldn't it? Because if it's decreasing speed, that means it's accelerating in the negative direction.
Right, but that just means, but you're right, if we were actually doing the problem, it would. But all we're doing is setting up just the equations of motion, right? And so in that case, it wouldn't matter. A is going to be negative when we solve for it, but we won't even see that now, right? So what would the equations be then? Is there going to be a horizontal net force? No, there are no components in the horizontal direction, so 0, right? Okay, what about vertically? What's our equation of motion going to be vertically? Yeah, good. So the upward force is going to be L. We're going to subtract mg, and what's that equal to? It's not equal to 0 this time. So the fact that it's moving upward, that it's decreasing speed is important. It also could have been increasing speed. Now, if it had said it's moving at constant speed, then we would have put a 0 there, right? But the fact that it's changing speed means there is an acceleration, and so that would be the answer right there. Yes, Lily?
The assignment on the rule marks it wrong if you don't include multiplication. Signs don't change.
Oh, it did?
Or sometimes it does, sometimes it doesn't.
Oh, okay. I'll go through and check them all, because it's...
You have to go to the keyboard and just press multiply.
Okay.
I didn't get it wrong.
Okay, there's a setting I can go in and adjust so it doesn't have to be, you don't have to put them there. I just probably didn't do it on these, so I'll fix that and regrade it. Okay, so there's that one. Let's look maybe at one, how about like this? So horizontal force F acts on a wooden crate. The crate slides across the floor in the positive direction with increasing speed. So it says include the appropriate coefficient of friction in your answers, meaning static or kinetic. Which one? Kinetic, because it's actually sliding. Okay, so then we make, again, a free body diagram, and this is a pretty straightforward one also. What are the forces acting this time?
mg downwards.
Okay, mg is acting downwards, good.
Normal force.
Normal force acts upward, good.
The horizontal.
Okay, so horizontal force, and it's moving in the positive direction. So that's going to be F, right? And then F sub k, right? So if we write our equations of motion down then, what are those going to look like? So we're going to get the x component of the net force is what?
F big F minus
F
F sub k.
minus F sub k, but, and that equals what?
U sub k times 4 normal.
Okay, good. So we're going to be able to make a substitution there. What's this all going to be equal to on the other side if the speed is changing? MA, good. So the only change we've got to make is that the kinetic frictional force, we have to write it using our model, which uses mu sub k, right? So we'd write this as F minus mu sub k times normal force equals ma.
How do you put that into the box?
Into the box, how do you find the mu?
Yeah, 'cause
You have to click on the square root sign.
Right.
And then there'll be a button with a bunch of Greek letters.
Yeah, there's gonna be, so you gotta open up the editor on these. So you click on that little icon to open up the editor, and then there's a menu with, I think it's got both capital and lowercase Greek letters.
how do you get the normal person?
How to get, because we know that this is always true. Kinetic frictional force always equals mu sub k times normal force. Okay? And they're telling us to write it using this stuff, right? So we can't just put in an F sub k. Okay? Now what about vertically? What's going on vertically?
Normal minus gravity is 0.
Good, it's 0 because there is no acceleration vertically, and that's just the context of the problem tells us that, right? Okay, last one. So that's what would go, this part right there would just go down and,
You just put 0 and then
yeah, put the equation. The equation is important here, right, because that's telling us that the normal force equals mg when we solve for it, which we need to know to substitute for normal force in equation 1. Yep.
So you don't have to put the 0 in the second equation, right?
No, you do. It has to be exactly like that,
Always.
right? And you see why now, right? Because if we were actually solving the problem, which you're not doing, we're done there, right? But if we were trying to find, for example, the acceleration, right? Well, then we'd have to know the magnitude of that force, so presumably that would be given to us, right? And the mu sub k would presumably be given to us, but we'd have to be able to plug in a value for normal force, which we would get from this equation, right? So we're not going any further than just setting up the equations of motion. You'd have considerable work to do to actually finish the, seal the deal here, but I'm just getting you some practice just setting up these equations of motion. That seemed like something people needed a little practice on. Okay? Questions on that? Okay, how about one like this? This is a little tougher because there's an angle. Okay? So a person drags a small dense object across the level ground at increasing speed with a rope that makes an angle of theta with the ground. Okay? So this is one where technically we probably want to make two free body diagrams. We want to make our original, and then we want to have an orthogonalized free body diagram where everything is broken into the appropriate components. In this case, just x and y components, right? So in free body diagram number 1, somebody tell me what's a force acting there? What's a force?
Gravity.
Gravity. Okay, point straight down, right? So straight down, we got mg. Give me another one. Sorry, give me another force acting there.
Normal.
Normal force. Which direction? Straight up. Good. Okay, give me another one. Yes, sir. Give me another. Rylan, which direction is friction acting?
To the left.
To the left. Good, because we're moving in the positive direction, right? So we've got F sub k, and we'll write that in terms of mu, right? And then last force?
Tension.
Tension. Okay, now what about tension? What direction is that acting?
Theta.
At the theta angle.
Okay, so there's theta, and that's tension, right? So the only thing we have to do to orthogonalize this free body diagram and make everything right angles, there's only one force that we have to break into components, right? So this is going to become, if we rewrite this thing, all this stuff stays the same. Normal force, frictional force, mg, but what else do we get?
The t cosine theta.
Okay, good. So this is going to be, this horizontal component is going to be t cosine theta, right? Because if we were to break this up into components, like if I were to break it up into a horizontal component and a vertical component, isn't this one going to be t cosine theta? Because it's the adjacent leg is the component. And by SOHCAHTOA, cosine goes with adjacent, right? And so this one would be t sine theta. Now, where does that one go? Ah, good, it's a vertical force, so we're just gonna superimpose it on top of that one, right? So now we can write our equations of motion. Okay, so what is going to be then, what's the x component of the net force?
T cosine theta minus
Minus
mu.
f sub k, right? And that equals what?
MA.
Oh, MA, but then, okay, MA, and then we can make this trade, right? We know that F sub K is just mu sub K times normal force. That's what friction is, right? So this one's gonna end up being, our final answer is T cosine theta minus mu sub K times normal force equals MA. So that's answer one. Okay, what about the vertical forces?
Normal plus tension of sine.
So we got two positives, right? Okay. Then we got T sine theta. And either order, it doesn't matter. T sine theta plus normal force. Addition's commutative, we don't matter which order we add them in, right? Makes no difference. Minus mg equals what?
Zero.
0. Good, because there's no acceleration in that direction. Very good. So that's our second equation. That's all we want. Right? Just setting them up. Okay? Good? Go back to it.
Is that it?
Yeah, I just wanted to go through those. Now you can.
Wow. Wow. This is a miracle.
Yeah.
I mean,